This quiz focuses on understanding how the BayesianRidge model from Sklearn works, especially in situations where predictor variables are strongly related, multicollinearity. We will examine its behavior in handling this challenge. This question tests your understanding of the BayesianRidge model's strengths and limitations. Specifically, I'll check your knowledge of its ability to prevent overfitting, how it uses its hyperparameters, and if it can deal with missing values by itself. This statement is true. BayesianRidge uses a technique called regularization, which helps prevent overfitting. It does this by adding a penalty to large parameter values. This is especially useful when variables are highly correlated, like in multicollinearity, because ordinary least squares, OLS, becomes unstable and easily overfits the data. This statement is false. The hyperparameters in BayesianRidge relate to the precisions of the prior distributions of regression coefficients and the intercept. They don't directly control L1, lasso, or L2, ridge regularization the way they do in lasso and ridge regression models. This is true. Unlike methods that only provide a single best guess for parameters, BayesianRidge gives you a whole distribution. This is cool because I can directly see how uncertain I am about my parameter estimates, which offers uncertainty quantification. This statement is false. BayesianRidge, just like most regression models, cannot handle missing data directly. I must pre-process my data and handle those missing values before using BayesianRidge. In this quiz, I need to identify which statements about BayesianRidge are correct based on my understanding of its features. I'm evaluating the BayesianRidge model, a type of regression model from Sklearn. It's a Bayesian approach to regression, which means it incorporates prior beliefs about the model parameters into the estimation process. This is particularly useful when dealing with datasets that have lots of correlated predictor variables, multicollinearity, a situation where simpler regression models can struggle. I'm assessing the validity of different statements about BayesianRidge. The quiz tests my understanding of its characteristics related to regularization, hyperparameters, uncertainty, and how it handles missing data in the presence of multicollinearity. This statement is false. BayesianRidge, like most regression models, doesn't automatically deal with missing data. I need to pre-process the data, perhaps by filling in the missing values, imputation, or removing rows with missing data, before using it with BayesianRidge. This statement is true. A key strength of BayesianRidge is its ability to give me not only best estimates of the model's parameters, but also the full probability distribution of those parameters. This means I get a measure of my uncertainty about the accuracy of those estimates, which is incredibly valuable. This statement is false. The hyperparameters alpha_1 and alpha_2 in BayesianRidge relate to the precisions of the prior distributions on the regression coefficients and the intercept. They don't directly control L1, lasso, or L2, ridge regularization like they do in lasso and ridge regression. This statement is true. BayesianRidge uses prior distributions on model parameters, causing shrinkage towards zero. This built-in regularization prevents overfitting, especially helpful with multicollinearity where OLS can become unreliable. I'm focusing on BayesianRidge regression, a specific type of regression analysis found in the Sklearn library. It's a powerful tool for handling data where the predictor variables are related, a situation called multicollinearity. I'll evaluate several statements about how BayesianRidge handles this type of data. Each statement will test your knowledge of how it works and what it can do. This is a simple answer indicating whether a statement is correct or not. In this context, I use true to indicate the statement's accuracy. Again, a simple way to tell you a statement is correct. I use false to signify an incorrect statement in the quiz. Another way to say a statement is wrong. Statement B claims that alpha_1 and alpha_2 directly control the L1 and L2 regularization. That's incorrect. These hyperparameters in BayesianRidge don't work the same way as in lasso and ridge regression. They're related to the precision of the prior distribution for the regression coefficients and the intercept. Statement C says BayesianRidge gives you the posterior distribution of the model parameters. That's absolutely right. That's a key strength because it shows how certain we are about the estimates. This statement says BayesianRidge is better at avoiding overfitting compared to ordinary least squares regression, OLS. I agree, because BayesianRidge uses regularization through a prior distribution, which shrinks the parameter estimates toward zero. It's less likely to overfit. I'm focusing on BayesianRidge regression, a specific type of regression analysis using the Sklearn library in Python. It's a powerful tool for predicting a continuous target variable based on input features. I'll be exploring its properties, particularly in situations with multicollinearity, when predictor variables are highly correlated. I find Bayesian methods particularly useful because they provide a richer understanding of the model's uncertainty. This section presents a multiple-choice question about the BayesianRidge model in Sklearn and its behavior under conditions of high multicollinearity among the independent variables. I'll evaluate each answer choice, considering the theoretical underpinnings of the model. This is the core problem statement. I'm given a scenario, using BayesianRidge on data with high multicollinearity, and asked to determine which statements about its behavior are accurate. Multicollinearity is an important context because it can cause instability in ordinary least squares regression. Statement A claims that BayesianRidge regression is less prone to overfitting than ordinary least squares, OLS, because of regularization. I'll check if this is correct. Overfitting means the model performs great on training data, but poorly on new, unseen data. Statement B says that alpha_1 and alpha_2 directly control L1 and L2 regularization. I need to understand what these hyperparameters actually do in BayesianRidge. L1 and L2 regularization are techniques to prevent overfitting by adding penalty terms to the model's cost function. Statement C states that BayesianRidge gives posterior distributions of the model's parameters and can quantify uncertainty. This is a crucial advantage of Bayesian methods, as it provides more than just point estimates. Statement D asserts that BayesianRidge handles missing data automatically. I'll need to verify if this is true. Imputation involves filling in missing values. It is usually a necessary preprocessing step in many machine learning models. This section introduces the core machine learning model, BayesianRidge regression. I will be assessing its properties to answer the quiz questions. This refers to the input data for the model. We have features, independent variables, and a target variable, the dependent variable we are trying to predict. This describes the outputs from the model. We'll get predictions, the model's estimates of the target variable, and posterior distributions, probabilistic estimates of model parameters. The posterior distributions are central to the Bayesian approach, reflecting uncertainty in parameter estimates. I see, you're asking about the truthfulness of statements related to using BayesianRidge regression, a method from Sklearn, specifically when there's high correlation between predictor variables, multicollinearity. We need to check which statement is correct about this approach. Cool. This statement is false. Unlike lasso and ridge regression, which have explicit L1 and L2 parameters, BayesianRidge uses alpha_1 and alpha_2 to control the precisions of the prior distributions of the regression coefficients and the intercept, respectively. These hyperparameters indirectly influence regularization, but they don't directly control L1 and L2 regularization strength. That's incorrect. BayesianRidge, like most other regression models, cannot directly handle missing data. You'll need to pre-process the data and deal with the missing values using techniques such as imputation, filling in the missing data, before applying the BayesianRidge model. Got it? I'm going to explain BayesianRidge, a regression technique found in the Sklearn library. This is a useful method that addresses the challenges of multicollinearity in regression tasks. Let's get started. This statement is true. A major advantage of BayesianRidge is its ability to provide not just point estimates but also the whole posterior distribution of parameters. This gives you a measure of uncertainty in your parameter estimates, which is very beneficial. This is also correct. BayesianRidge uses a prior distribution on the model's parameters that shrinks them towards zero. This implicit regularization helps prevent overfitting, especially helpful when predictors are highly correlated. OLS doesn't inherently regularize and therefore can be unstable when there's high multicollinearity. I visualize BayesianRidge as a machine learning model that uses Bayesian statistics. It's like a detective who uses prior knowledge, beliefs about the data, along with new evidence, the actual data, to solve a mystery, predicting outcomes. This architecture is particularly well suited to data with multicollinearity, where traditional methods may struggle. The model uses a process called Bayesian inference. Think of it as a refinement of its initial beliefs based on the observed data. It doesn't just give one answer, but rather a range of possible answers with their associated probabilities. This is very helpful when you want to understand the uncertainty inherent in your predictions. This is the result of model inference. It's not just a single best guess, but a probability distribution for all the model's parameters. It tells you not only what the best estimates are, but also how certain you are about those estimates. That's the key advantage of Bayesian methods, that you get a complete uncertainty picture, not just a point estimate. Before seeing any data, I have some initial beliefs about the model parameters. These parameters define the relationship between input and output. These beliefs are represented by a prior probability distribution. For example, I might believe that the parameters are close to zero, which encourages regularization and prevents overfitting. This prior is combined with the data to obtain a posterior distribution. This refers to the dataset that I'm using to train the BayesianRidge model. Multicollinearity means that some of my predictor variables are highly correlated. It's like having multiple witnesses to a crime who are all telling a similar story. While not necessarily a bad thing, it can make it difficult for some regression models to determine the impact of each witness individually. This is the problem statement. I am asked to analyze a few statements about the BayesianRidge model's behavior, especially in situations with multicollinearity. It challenges my understanding of Bayesian methods, regularization, and parameter estimation. I'm working with the BayesianRidge regression model, a specific implementation of Bayesian regression found in the Sklearn library. It's a powerful technique that cleverly combines the advantages of Bayesian statistics and regression modeling. I'm presenting a multiple-choice question about the BayesianRidge model in Sklearn. We'll explore its properties and how it handles multicollinearity. This is the core question. We're testing your understanding of the BayesianRidge model's behavior when dealing with datasets where predictor variables are highly correlated. This is a common challenge in regression analysis. Statement A is true. BayesianRidge inherently regularizes its model parameters, preventing it from overfitting to the training data, unlike ordinary least squares. This is particularly valuable in situations with high multicollinearity. Statement B is false. And in BayesianRidge don't directly control L1 and L2 regularization like in lasso and ridge regression. They control the precisions of the prior distributions of the regression coefficients. Statement C is true. A key feature of BayesianRidge is its ability to provide estimates of the full posterior distributions of its model parameters. This provides a measure of uncertainty around the parameter estimates, which is very useful. Statement D is false. BayesianRidge, like most regression models, requires that you've pre-processed the data, handling missing values before fitting the model. It does not inherently handle missing values.